In this lecture, we study the algebra. So this is a paper number 8, algebra 2. In the last semester, we have to study what is the algebra 1. So what is group? So we have to study in the last semester. So what is a group here? So G is any non-empty set and star is any binary operation. Then G star is called group with satisfying some axioms. So that is one closure property. So what is closure property? If A and B are the elements of G, then A star be also element of G. So star is the binary operation between A and B. Okay, what is the closure property? So first axiom, so first property is what? A and B are the elements of a group of a G. G is any non-empty set. Then A star B belongs to G also. So this is a closure property. Then second property is what? Second axiom. So associativity. If A, B, C are the elements of a non-empty set G, then A into BC is equal to AB into C. So A into B or A star B into star C is equal to A star B star C, where star is the binary operation. Okay. Then what is the property of existence of identity? So what is the identity? If A is an element of a set, non-empty set G, then there exists an element E belongs to the set G, then A star E is equal to A is equal to E star A, then E is called identity element. Means, repeat again. So A star E is equal to A itself, is equal to E star A, then E is called identity element. Okay. Then what is the next axiom or property? So that is fourth property. So what is the existence of inverse? If A is an element of G, then there exists another element B of G such that AB is equal to BA is equal to E. Then B is called the inverse of A. B is called the inverse of A. So the algebraic structure G star is a binary operation. G is a non-empty set. So G star G satisfying the properties: one, closure, commutativity, then existence of identity, then existence of inverse, then the set G is called a group. So we just, what is the definition of a group? So now we study here. So what is the Lagrange's theorem? So you know what is the order of G. So order of G nothing but how many elements in a set G. So that is the order of G. So we study here what is the relation between. So H is any non-empty set of G. H is any non-empty subset, or H is a subgroup of G. Then if we consider the order of both sets H and G, so order of H and order of G, so H is a subgroup of G, then order of H and order of G, then what is the relation between the order of H and G? So that is the Lagrange's theorem here. So that is the Lagrange's theorem. Okay. So what is Lagrange's theorem? If H is a subgroup of a finite group G, if H is a subgroup of a finite group of G, then order of H divides order of G. Order of H divides order of G. So what is the order of H here? Order of H nothing but the number of elements in set H. Okay. So H is a subgroup. So order of H nothing but the total number of the elements in members in H here. So order of H divides order of G. So this is a theorem here. So this theorem is the Lagrange's theorem. So what is the proof here? Let G be a finite group of order n and H is a subgroup of G. Okay. So that is given here. Okay. So what is the case? Suppose H is an improper subgroup of G. H is an improper subgroup of G. What is improper subgroup? So let us take an example. So suppose H is an improper subgroup of G. So improper means what here? If H is only one element, so that is a singleton, that is E. Only one element is there. So H is a subgroup of group G, and H having only one element, E. Then order of H is 1. Because there is one element only, so order of H is 1. But order of G is what? Order of G is what here? N. We consider order of G is N. So certainly, no doubt, so the order of 1 divides N. Order of H is 1, order of G is N. So certainly, clearly, 1 divides N. So in this case, order of H divides order of G. Okay, so what is the next? So if H is G, H is equal to G, means subgroup H is equal to the group G. Okay, both set are same here. Then order of H is N, also order of G is N. Therefore, N divides N. N divides N. Therefore, in this case, order of H, certainly N divides N, implies that what? Order of N means order of H divides order of G. Okay, clearly. So if H is an improper subgroup of G, then this is proved here. So hence the theorem is proved in this case. Order of H divides order of G here. Okay. So in this case, order of H divides order of G. Okay. So what is the case 2? In this case, H is improper subgroup of G. So in second case, suppose H is a proper subgroup of G. Proper. So what is the improper and what is the proper? You understand what is the improper and what is the proper subgroup of G. Suppose H is proper subgroup of G, and let order of H is M. Order of H is M. Okay. Let A belongs to G. B and A is an element of G. Then HA is a right coset. HA is a right coset. What is the left coset? A into H is a left coset. HA is the right coset. So we given the definition of right coset here of H in G, that is HA is equal to H1 into A, H2 into A, H3 into A, and HM into A. So H1, H2, H3, HM are the members of subgroup H. So what is the right coset? So HA into H1, H2A, H3A, and so on, HMA. Since order of H is M here. And there are M distinct members are there. So have M distinct members. Okay. Let HA, H. So this is one. This is what? This is one right coset. One right coset. Multiplying by A to H from right. So this is a right quotient. And this is a definition. So this is a right quotient. So we take here HA1, HA2, HA3, HAK are all different right cosets. Are all different right cosets of G, of H in G. Okay. So these are the distinct K right cosets. So what is G? So G is the set of union of all those right cosets. So HA1 union, HA2 union, and so on, union of HAK. Okay. So then what is that? We take order of both sides here. Order of both sides. So what is the order of G? Order of G means order of HA plus order of H, this right coset, order of this right coset plus order of this right coset plus and so on, order of this right coset. But what happened? What is the order of H? What is the order of H? Order of H is M. Order of H is M. So order of H is M. So what is the order of this right coset also m. Order of this right coset also m. So what is the order of this right coset? Also m. Order of this right cosets also m. M. So m plus m plus m plus m something किंवा what happened here? Order of just what is the order of h is m. Okay, but order of h and order of subgroup h and order of right coset is same m same. So what is the order of ha? Nothing but order of h. Order of ha nothing but order of h. So order of ha2 this right coset nothing but order of h. So this is order of h. So how many times? So this is k times. This is k times here. Okay. Then k times. So what is this? So this plus this plus this plus this k times. So this is what happened here. So order of g is equal to k times order of h. Okay. Order of g is equal to k times order of h. So what is the order of g? Order of g is n. That is given. Order of g is n. So k times what is the order of h? M. So this implies that m divides n. This implies that m divides n. What is m? This is the order of h. What is n? This is the order of g. So in this case, when h is a proper subgroup of g, order of h divides order of g. So also we, in case 1, we prove also order of h divides order of g. So both cases we prove the theorem. Okay, if each h is a subgroup of a finite group g, then order of h divides order of g. So this is the Lagrange theorem. Okay, so this is a very simple proof here. So now, what is the index of a subgroup? So now, what is the definition of index of a subgroup? Just index of subgroup. So H is a subgroup of G, then what is the index of subgroup? H with respect to G. Index of subgroup. Okay. Let G be a finite, G be a group. And H be a finite. So H be a finite, be a simply not necessary. Can G is a finite, then H must be finite. So let G be a group and H be a subgroup of G The number of distinct right and number of distinct right or left cosets of H in G is called index of H in G. So it is denoted by the symbol. So what is the symbol here? Index of G is denoted by index of H in G denoted by IGH or simply GH. So this is the notation here. So what is the definition? Let G be a group and H be a subgroup of G. Then number of distinct right or left cosets of H in G is called the index of H in G, okay, and it is denoted by this symbol here, okay. So we take what is the example, and we understand what is the index of a group, okay. Take an example. Let Z plus is the binary operation, Z is a set of, be a group of integers, let H is the subgroup of Z, defined like that 3n. It is a set of, H is a set. It is a set of all such 3n where n are the elements from integer, be a subgroup of G, find the index of H in G, okay, index of H in G. So what is the solution? So we find an index of the subgroup H in G. So H is given, Z is given. Let Z be a set of integers. So that is, what is the integer set of? Something -5, -4, -3, -2, -1, 0, 1, 2, 3, and so on. So this is a set of integers here, okay. So Z is equal to. So what is the subset? What is the subgroup H? What is the subgroup H of H of G? So that is given here. So H is the set. It is set of all such 3n where n belongs to Z. The right coset. So we find here the right cosets with respect to the binary operation plus. Okay, right cosets. The right coset of H generally containing M is given by, okay, containing M is given by H plus M. So this is right coset. So before that we write there HA is equal to something what happened here, H1A or H2A or so on, HMA, where there are M elements are there, okay. So this is the right coset. In between this there is a star operation, multiplication, or we don't know. So HA, here we write this like that, something H plus A, M. We take in this, there is a star operation, in this too there is a plus binary operation, so this is the right coset. So adding M rightly to in H, okay. So what is, let we take M is equal to 0. We take I think H, M, take M is equal to 0. Then what happened? H plus M, nothing but what? So that is H. So H, nothing but. So what happened here? So H, what happened? So this is 3n. So the elements of this, so multiplying 3 to each element of this element. So this is Z. So multiplying 3, so that is 0. Multiplying 3, -3, then -6, -9, and so on. Then 3, then what? 6, 9, and so on. Okay. So this is H. M is equal to 0. So H plus 0. So that is H again. So this is a subgroup of group G. So this is subgroup of group Z. So H is a subgroup of group Z. Z is a set of integer here. Okay. So this is H. We take now M is equal to 1. Then what happen? M is equal to 1. So what is H plus 1? So these are the, so this is the right coset. Adding 1 from right in H. So that is right coset is what? So add 1 in each element of H. So what happened here? So this is what happened. So that is add 1. So this is minus 9 plus 1, minus 8, minus 5, minus 2. Then what happened? 1. Then plus add 1, 4, plus add 1, 7, then 10 and so on. Okay. So this is right coset. Okay. With respect to binary operation star. So here is a star operation is there. It may be multiplication, it may be addition, any. We don't know. Okay. Particularly we take here addition operation plus. Particularly we take addition operation. So if we take M is equal to 2, so H plus 2, then what happen here? So add 2 in each element. Then what happen? Minus 7, minus 4, add 2, minus 1, 2, 5, 8, then 11 and so on. Put M is equal to 3. Then another right coset H plus 3 is equal to what? Minus what? Add 2 here. Add 3 here. What happened? Add 3. So minus 9. Add 3. Minus 6. Add 3. What happened? Add 3. Just minus 9. So add 3. What happened? Minus 9 plus 3. That is minus 6. So before minus 9. So add 3. 0. Add 3. 3. Add 3. 6. Add 3. 9. And so on. Okay. So then put M is equal to 4. Then H plus 4 is what? Similarly. So adding corresponding element 4 in each element. So what happened here? So this is minus 5, minus 2, and then 1, 4, 7, 10 and so on. So again, M is equal to 5. Then what happened? H plus 5 is equal to what happened? So adding 5 in each element, we get here minus 7, minus 4, minus 1. So that is 2, 5, 8 and so on. So these are the right cosets of H in Z. G is what set? So that is a set. Z is a set of integer. But we observe here. So we observe that. We observe that. What happened here? So H plus 3 and H. These two sets are same. Means this right coset and this right coset. So what is this? H plus 0. So this is also right coset. H is a set, but H plus 0 is also right coset. So this and this same. So that is H plus 3 is equal to H. Again, what happened here? H plus 3. H plus 4. So H plus 4, this and this is same. H plus 4. So that is H plus 1. What is H plus 2? H plus 2 is equal to what? H plus 2. Both sets are same. So this right coset is equal to this right coset. So H plus 5. So and so on. So the right cosets are repeated. So how many different right cosets are there? Only 1, 2 and 3. Only 3 distinct right cosets of H in Z only. There are only 3 right cosets. All right cosets are repeated. So we proved here. Okay. So what is the index? Index of H in G. So how many distinct element of right cosets of H in G? So there are only 3 elements. So index of this set in Z is 3. Thus we get only three right cosets, only 3 right cosets. Therefore the index of H in Z is 3. So this is the very simple example. Okay, so you understand also definition of index of subgroup F in G. So this is very simple definitions. Okay, so what are the consequences or applications of Lagrange's theorem? So there is a corollary. So what is the consequences of Lagrange's theorem? So we take a theorem, another theorem. So on corollary, we say it is a corollary. Okay, corollary. The index of any subgroup the index of any subgroup is a divisor of the order of group. Index of any subgroup. So H is any subgroup. Then we find index of that subgroup. Then the index also divides the order of group G. So okay, proof. So very simple proof here. Okay, simple proof. Not necessary to give here proof of the this corollary. Let G be a finite. Let G be a finite group of order n. Let G be a finite group of order n, and let H be a finite subgroup of G of order m. Say so order of G is n and H is a subgroup of G of order simply small m here. Then by Lagrange's theorem, what is the theorem? Just we prove Lagrange's theorem. If H is a subgroup of G, then order of H divides order of G. So this is a Lagrange theorem. So then there are n something. There are the number of distinct right cosets. Then there are just what happened here. That is, so index of G H is equal to, so this is a notation H G. So that is by Lagrange's theorem. So order of G divides order of H. Order of G divides order of H. So this implies that what happened? So order of G is equal to index of G H into order of H. Okay, order of H. Then what happened? So this implies that. So this is by using. So this is the theorem, Lagrange's theorem. So we say it is index of H in G here. Index of H in G. So this implies that what it implies. So index of H by using this index of H in G divides order of G. Order of G. So this proves that the index of any subgroup H of G is a divisor of the order of the group G. Order of the group G. So what is this? The index of any subgroup is a divisor of the order of group G. Order of group G. So that is the proving here. So what is the index of subgroup of G? And we take example. So what is the index of subgroup H of G here? So, and this is a very simple theorem. So we stop here. In the next lecture, we see some another consequences of Lagrange's theorem, and we take some examples. Okay, so you remember. So what are the some theorems are there, corollaries are there, definitions are there. So it is better to understand those theorem or definition by using example. It is the best way. Thank you.